Hello, WeAreDevelopers. It's great to be here. We will be talking about how to integrate Rust with other languages to get the best of both worlds, to supercharge your existing app with native superpowers. I'm Harald. I'm a software crafter and a 3D graphics engineer at Dellos Healthcare. At the moment, I'm on parental leave. I'm a big hiking fan, and also I'm organizing the mob programming and open source software meetup together with Fred and other great co-organizers. You can reach me on Twitter. My DMs are open. Feel free to reach out, ask any question.
All right. Hi, I'm Fred. I'm a software engineer. I work on Power DNS at Open Exchange. I co-organize the Rustic mob programming meetup, where we do mob programming using Rust. I love scuba diving. You can find me on my website and on GitHub. All right. So why would you want to integrate Rust with other languages? What I will be talking about is primarily integrating something that's written in Rust from C and from C++. Perhaps you want to develop your application logic in a performant, memory-safe programming language, but then you want to build the UI around it using GTK and C or Qt and C++. Perhaps you want to incrementally modernize a code base, one module at a time. All right, I will be using a priority queue as a working example. The priority queue is backed by the binary heap implementation available in the Rust standard library. The reason I chose the name priority queue is to not confuse between the memory heap and the binary heap. All right, so a priority queue works by putting elements into the queue out of order, and when you pop them out, they come out in sorted order. What we will do is we will build a foreign function interface, FFI for short, around our priority queue implementation. All right, so let's look at some C code on how to use our priority queue. So we call the constructor, we pass the constructor elements from an array, and then we have to pass the number of elements in that array. This is pretty standard C coding style. We check for null, and if that's the case, we fail. And then we loop a few times, and we start popping stuff out of our queue. We get back a return value in the form of a struct. This struct contains two members, a value, and a status code. The status code could be one of three things. If it's success, it means the value contains something relevant. If it's empty, it means we try to pop something from an empty queue. And if it's invalid argument, it means we passed an invalid argument to the pop function, such as a null pointer for the queue. All right, we switch over the status. If it's success, we print the value. If it's empty, we print nothing. And if it's invalid argument, we fail in some way. We free our queue. And then if we try to run this, we see that it works correctly. And because we popped more times than we have elements in the queue, then we have like nothing printed out. OK, this is how the C header file for our queue might look like. The thing to take away here is that the struct for the queue is a forward declaration and is behind, meaning that it's an opaque struct. We don't really have access to the details of that struct. All right, a few things we need to know before we continue. Rust guarantees cannot hold across language boundaries. Rust mangles function names, and we can use the no-mangle directive on a function to stop the Rust compiler from mangling its name. Rust does not follow the C or the platform's calling convention. You can use extern C or extern system to ask the Rust compiler to generate code for that function that follows the convention. Some Rust types are not FFI safe. Things like slices and tagged enums cannot be passed around to C back and forth by value. Struct and enums with the Rust representation don't really have specified layouts. And to get a C-like layout, we have to use the repr-c directive on a struct or on an enum so that we can pass it around by value. All right, let's take a look at how we might implement our constructor in Rust. So this is the C API, and this is the queue, and it's backed by the binary heap, which I mentioned before. And then this is the signature for the constructor of the queue. It takes the elements array, and it takes the number of elements in that array. What seems surprising here is that we're taking the array as an option reference. And this works because references are non-null. And so the Rust compiler is able to take advantage of that fact and represent the options none using null. Or in that case, in that case, it can represent null using the options none, right? Depending on which way you look at it. All right, so another thing that might seem a bit strange is that we're returning an option box queue here. So any box with carrying a type T, and T is sized, is guaranteed to be represented as a reference. And so an option box of T, where T is sized, is guaranteed to have the same representation as a raw pointer. OK, so we create our queue, and at the end of the function, we box it onto the heap and return it. And then we extract the reference to the array, and then we create a slice out of that reference using standard slice from raw parts. We have to pass that the elements reference and the number of elements that we expect to be there. This function is obviously unsafe because the Rust compiler can't guarantee that len is actually correct. It can't guarantee that it's really the number of elements behind that reference. We loop over the elements. We loop over the slice we just created. So we loop over the elements, and we push them one by one into the queue. We slap extern C, as I've mentioned before, and no mangle to get the C calling convention and to stop the Rust compiler from mangling the name. All right, let's look at pop. This is the struct. This is the return value struct that we've seen before, and this is the status code enum that we've also seen before. The only difference is that they're implemented in Rust, and they have repr C slapped on top of them to be able to pass them by value to the C side. So the pop implementation, there's nothing really special here except that we return this PQU8 value struct by value. We check if we got a null pointer for the queue. If that's the case, we return invalid argument with some dummy value. And then if not, then we try to pop from the queue. And if that works, then we return success with the value that we popped from the queue. And if we couldn't pop anything from the queue, meaning the queue is empty, then we return empty and some dummy value. OK, the free function for our queue takes the queue by ownership. So it moves ownership from the caller into the free function. And because it's an option box, it means that if there's something inside this option, this thing will get freed when the scope of this function exits. But if it's none, then nothing really gets dropped. So we don't really try to free a null pointer. OK, this is how it looks like if we run our small example in Valgrind. So Valgrind is this memory checking tool. And we can see that it works correctly. There are no invalid memory accesses, and there are no memory leaks. OK, now we'll look at C++ bindings using the CXX crate. So CXX is this really amazing crate that can generate Rust bindings from C++ bindings from Rust code. And this is done without the programmer maintaining C++ wrappers around the C API. So CXX takes care of that. And it does that by providing implementations of Rust types in C++ and providing implementations of C++ types in Rust. Let's take a look at how we might use our Q C++ API from C++. So we call the constructor, and we pass it elements. Elements is a Rust slice, and it's backed by a standard C++ array. We loop a few times, and we pop from the queue, and we print out the values that we pop. And then we use exception handling to handle errors, such as the queue is empty. And we print out the exceptions message, if that's the case. OK, now let's take a look at how we might implement that in Rust. We have to provide declarations first. So CXX works by providing the CXX bridge macro. So what we do is we create this FFI submodule inside of our queue module, and we slap the CXX bridge macro on it, and this macro is what really takes care of most of the magic. Inside of our module, we provide an external Rust block. We can also provide an external C++ block. The stuff that is outside either of those external blocks are shared structures between Rust and C++, meaning they can be passed around by value. And the stuff that's inside the Rust external block are declarations for Rust implementations. So they are declarations for stuff that will be implemented in Rust, and meaning that the C++ side doesn't really get access to implementation details. And stuff that is in the external C++ block are declarations for things that will be implemented in C++, and the Rust side doesn't really have access to the implementation details. We don't really concern ourselves with external C++ here because that's not relevant for our use case. All right, so inside of the external Rust block, we declare our queue. We declare the constructor. And notice that the constructor takes a idiomatic Rust slice, like you would expect, and returns a box. And then we implement the pop method, and also it returns result, which is idiomatic Rust. The error type for the result is implicit in the declaration, not in the implementation. And any error type that implements the display trait can work here. All right, let's take a look at the implementation. So this is our queue that we've declared previously. The constructor, again, it takes a slice and returns a box, pretty idiomatic Rust. And the implementation is also idiomatic Rust. So we're not relying anymore on standard slice from raw part, which is unsafe. So we're not relying on unsafe code anymore. And we're taking a slice instead of two separate values, one for the array pointer and one for the length of that array. And then for the pop implementation, we return a result of either U8, and the error type here, I picked a static string for simplicity, and that's the error type I mentioned earlier. And the implementation is also pretty idiomatic. So we try to pop from the queue, and if we found something, then we return it. And if we couldn't pop anything because the queue is empty, we simply return the static string, queue is empty. All right, and we can see here that it works. The exception message is printed, pop error, queue is empty. And then we also see that there are no invalid memory accesses, and there are no memory leaks. Thank you very much. And I left references here. And I will hand over to Harald. Thank you.
OK, let's have a look how to do this from Java. Why would you use access Rust from Java? So yeah, the cool thing is you get the advantages of the managed world and also the power and performance of the native world. Or you can access low-level drivers or APIs like OpenGL or Vulkan or any hardware stuff. OK, let's try this and access the queue thread presented via JNI. Where do we start? First, we have to declare native methods in Java. That's actually pretty simple. We, for example, create a Rusty priority queue in a collections package. Then we declare a method pretty similar like you would declare an interface method, except that we also add the native keyword in the front. And then we can just call it and, for example, pass the elements array in the constructor. Native methods are actually just functions, so they are not aware of any object state. There is a workaround for that. We can return a pointer from the native side and store it here, as a long member. And we will use it later for subsequent method calls. Like, for example, here in the push implementation, it's similar. The main difference is here we pass the object pointer so that the native side can reconstruct the native priority queue object. Yeah, and here we've just forward the push method to the native push function. The pop implementation is also pretty straightforward, nothing new here. The free implementation is maybe a bit more interesting. So we will call free on the native side, and it will clean up the memory that was allocated. What we need to do is to invalidate the pointer and make sure that we don't use it afterwards. For example, we can set it to 0. One might also want to use finalizer, which are kind of like destructors in Java, but it's not recommended to use them. They're also going to be deprecated. This is why we need to call destroy explicitly and make sure that we are not using the object afterwards. Of course, we also have then to check if it's already 0. For example, in the code I showed you before, we have to add this check for null and throw, for example, an illegal state exception. So let's get rusty. In order that Java knows which function to call, or we provide the right function that Java can call, GNI defines a name mangling specification. You can look it up, or what is probably more convenient is you generate a C++ header file. There is a flag for the Java C compiler which lets you do that with -h. And then you get a C header file, and this is like the function declaration, how it looks like. You can see that it encodes also the package name and the class name. It's pretty ugly to read, and it passes a couple of GNI-specific parameters. These types are defined in the GNI header file. But on the Rust side, we don't have this GNI. We cannot use this GNI header file. But there is the JNI crate, which provides the necessary types and logic. So we add it to our dependencies in the package definition file. And now we can declare the function which can be called from Java. It gets an object of the Java environment, which we need. Also the J class, which we don't use. That's why it's prefixed with the underscore. And the byte array from Java. Then we have also to add this no mangle and extern system. The function name is pretty ugly, not very developer friendly, but there is a rescue, and there is this very clever JNIFN library or crate. We add it also to our dependencies, and then it provides an attribute which you can use, and we pass as a string the package name and the class name as an attribute, and then we can define our function with a nice readable name, and we don't need to add this no mangle attributes. It's already included in the GNIFN attribute. Okay, so let's get to the implementation. We have to use this J environment to get the array from this J byte array object with the get byte array elements function, and we have to tell it it will return us a copy, and if we do changes, we have to tell it if it should copy back the changes. In our case, we are only reading, so we say no copy back. Then we can, from this auto array, we can get a pointer and the size of the array, which allows us to create the slice of memory, which we can use then for initializing the priority queue. We iterate over each element and push every element to our priority queue. Then we have to box the priority queue onto the heap. And with box into raw, we can convert it into a raw pointer. At this point, it's not managed by Rust anymore, so we can, if we would leave that out, the priority queue would be destroyed when it leaves the scope. But now we can leak this pointer to the foreign side because Rust is not managing it anymore. There is also an alternative to this get primitive, to this get byte array elements, namely get primitive array critical. The difference is get primitive array critical should not copy the array memory, but it might block the Java garbage collection until the returned auto primitive array is destroyed, which is the end of the critical section. I'm saying should and might because it depends on the JVM implementation, but for most implementations, this should be true. And yeah, if you have large data, you would want to avoid having to copy large data. If we change the previous example, we basically just need to change this function line and function call and the return type. The signature stays the same. We get the pointer and the size similarly, so we can easily try out both. For the push implementation, we have to cast the pointer which we receive from Java to the mutual PQI8 pointer, and then we dereference it and create a mutual reference from it. This is an unsafe operation, so we wrap it in this unsafe block, and then we can use the priority queue as before. And also we should add the null check also on the native side to be secure and don't have to rely that it's not called from Java with a 0. Yeah, the POP implementation is also very similar. The only thing is that we have to handle the case when it pops an empty stack. One idea would be to throw an exception back to Java. If you want to have a look how this can be done, we have the example on GitHub. Please check it out. A bit more interesting is how to clean up the memory, actually. We have to, again, cast the pointer, which we get from Java, to the mutual PQ pointer. Then we do the inverse operation, the box from raw. Now we tell Rust, we want you to manage this memory again. And then we can do a drop. The drop is actually not necessary as Rust is already managing it, and it would drop it anyhow when the scope of the function is left. But it might also be nice to have it explicitly like that. And we need to wrap it in an unsafe block. The only thing left to do is to load the library from Java. So what we can do is create a static initializer in our Rusty priority queue class, and then we call system load library to load the library we created from on the Rust side. This needs to be a shared or dynamic library, so a DLL or a .so file. So we have to define the crate type also with cdlib. You will find the references on docs.rs on the 2 main crates I've been using. There are also links included to the official GNI specification, and there are lots of examples. Rust is really example-driven. Every library comes with compilable, runnable examples included, so it's really good to check that out. There are also alternatives to JNI. There is the Java native access, which should be easier, but also slower. There is the newer Java native runtime. Apparently, it has comparable performance, and you don't have to handwrite all this glue code like with GNI. And there is also the project Panama, but it's still experimental, and yeah, maybe you want to check that out. A general rule of thumb you might want to consider is that also the JNI interface has a performance penalty, so you probably don't want to go over the interface for every array element. And yeah, you have to consider if the performance benefits might outweigh the performance penalty when going native. Okay, I prepared a little demo for you. I've implemented 2 image filters, which I'm executing on Java and on Rust. One is a blur filter, and the other one is a grayscale filter. So we have here this image of a baboon. This is how it looks like. And the main function of my Java class, it's loading the image, then it's measuring the time, it's calling, it's passing the pixels array to the grayscale filter, and the same thing happens for the blur filter. Let's quickly have a look how this is implemented. So we have the Java grayscale filter. Basically, it iterates over every pixel and then takes the red, green, and blue pixels and multiplies them together with these factors and sets all colors to the same value. And we have the same thing for Rust as well. So yeah, it looks quite similar, but this time it's Rust. And now let's have a look back at the main function. So we are using now the Rust filter. So and both of the Rust filters. Sorry for that. Let's execute and run it. Okay, so we see the grayscale filter took less than a millisecond. The blur filter took 3 seconds. Let's have a look at the result. So if you see, it's more blurry and it's grayscale compared to the original. And we can now quickly change it and say we want to have the Java blur filter and the Java grayscale filter. And let's run it again. And now we see, now it takes 7 milliseconds and 20 milliseconds, so it's 7 to 10 times slower in Java, because Java has all those runtime checks when accessing array and so on. I'm not a Java expert, so I don't know. It's also not a scientific measurement what I'm doing here. I'm running it just one time, so don't take the numbers for granted. But that's more or less, it gives you some impression of the difference. Yeah, so you can find the examples on our GitHub. Might want to check that out, and also the slides. Are there any questions?
Thank you very much. There are a few questions, though we don't have much time left, but you will be standing outside and answering the question, and also they will share the slides with you. So let's see if we have time. If you're using Java and Rust, will the object from the array held in the JVM heap?
Can you?
Yeah. If you're using Java and Rust,
yeah,
will the object be held on the heap of the JVM heap?
No, it will allocate it in a separate memory. So what you allocate in Rust will be in a separate memory, and Java basically doesn't know about it.
Okay. So let's see, we have time for one more question. How difficult it is to practice, in practice, to have both Rust and C++ code with FFI in the same code base handled through a single build system, such as CMake?
Okay. So there is an appendix which shows how to do the build-related stuff. In the interest of time, I did not put that in the main slides. But what I show here is basically how to manually create an SO file or a DLL, and then linking it and so on. But so that's for C. So for C, you're pretty much kind of on your own. If you're using the CXX crate, it has a lot of documentation on using different build systems, including CMake, and integrating with that. So check out the CXX crate. It's very well documented, and it's excellently implemented. So yeah.
Thank you very much.
Thank you.